Today, as we discussed in our last class, today in the next few lectures, we will review the basics of signals and systems and digital signal processing. So, what I plan to do is today and the next two lectures, or maybe even the whole of next week, will devote to digital signal processing. And what I want is there is supposed to be there are supposed to be two tests and then your mid and sem. So instead of a test, I will give you an assignment instead of a test. Instead of test one, I will give you an assignment to review digital signal processing concepts. And the assignment will be due by the end of this month. And the assignment will be due by the end of this month. So what I want is you review digital signal processing concepts, and next 3-4 lectures will discuss that. But you have to write an assignment, detailed one, in the next 15 days or so, and by the end of this month, 31st of August, uh, you submit the assignment, and instead of the test, that will be instead of the first test, that will be assignment. And please take it seriously, otherwise this course is going to be almost worthless for you, very painstaking for you. So that's it. So let's start. So these are the main things we have to cover: LTI system, Fourier transform, and Z transform. But let's start from the beginning. What is a signal? So any physical quantity which we can measure with respect to another physical quantity is a signal. Uh, I hope my voice is clear and audible enough. If you need, I will increase my mic output. Tell me my voice is increased, or should I? Is it audible enough? Type Y if it is so. Yeah, okay. So then I will go back to my this one. So any signal is nothing but a quantity measured with respect to another quantity. So, for example, here we take our speech as an example, which looks like this, and the axis is time. This is your amplitude. So we say, right, give a notation S. We said is an independent variable is t, and then speech is a signal, which is a function of time. So it is a signal. Now you can have an image as a signal as well. Let's take a black and white signal, a black and white image. So here, depending on what is the size of your image, pixels we call it. So pixels we call it. So let's say you might have this one. Let's say 1024 and 512. Let's imagine something like that. So 124 pixels in the x-axis and 512 in the y-axis. So any point is now signified by two spatial coordinates. In speech, you have time as a variable. In image, you have x and y coordinates as variables. And what are you measuring for a black and white image? You're measuring some intensity values, generally depending on how many bits you assign to a sample. It will come to, maybe you can revise all that on your own, but let's say 0 to 255 or 8 bits per sample you have allocated. So 0 to 255, any integer between that you can any of these pixels can take, and that becomes your intensity. So intensity, a black and white image, is a function of two independent variables x and y, and this is the signal representation of that. A color image is like three black and white images stacked together. So in black and white image, you have black and less black, gray, more gray, white gray, and it's called levels of gray or shades of gray. That's what a black and white is. 0 is black, 255 is complete white. In between, you get a shade of gray. In case of a color image, you will have shades of red by one of this. You can say it is a matrix which represents the shades of red, or there are three images on stacked on top of one another. One representing color red, one green, one blue. Let's say this one is red. Then let's say let's say this one is green, and let's say the other one is. So any point actually in a color image, a signal. This is called a three-channel signal. You must have heard the word channel, multi-channel. This is what a multi-channel signal means. Means at any value of independent variable x and y, you have at any point defined by the coordinates, independent variable coordinates. In our case, is an x and y. Then you will have three values in this case. One is for red, blue, and green. So this is called a multi-channel signal. So in this case, three-channel signal. In case of our speech, it's a single channel signal. But what is its dimension? The dimension is given by the number of independent variables. In the case of speech, there is only one independent variable time. In the case of image, there are two independent variables coordinates. Now you can have other things also. For example, I will erase this. Yeah, you can have, for example, you must have heard ECG, electrocardiogram. So there are lots of, you see, electrodes or lots of sensors. Channels is also a synonym for sensors. You need multiple sensors to have multiple channels. So if you record your signal, speech signal with multiple microphones instead of only one, then you can say it's a multi-channel signal. At any time, depending on where your microphones are located, if it is directly in front of you, you'll get exactly the same same signal. But if it is in odd places, the signal that is being recorded by the multiple microphones will be different, and that can be called as a multi-channel speech signal. But let's say now coming up to ECG, you might have seen a person with lots of wires, different positions in the body, they attach. So that is also multi-channel signal. Its position, it might be given by what's independent variable, could be time. Generally, it's time, but this is multi-channel signal. So depending on the number of electrodes you fit in your body, in biomedical engineering, ECG signal comes up with multi-channel. Generally, there are 12 channels nowadays, but there were also 8-channel ECG, 4-channel ECG, depending on how expensive your uh, equipment is. So that's what signals is. So I hope you got what signals is. So I will erase this. So now, what is a system? A systems is something which is used to manipulate a signal, whether we desire it in a way it is desirable to us, or it is not desirable to us. but it's something that will manipulate a signal. So in the case of, for example, speech signal, so suppose the speech signal is corrupted by noise, so there is some background noise which corrupts it. You might want to have a system which filters out, removes this noise, and retains this speech signal, the one which you want, as closely resembling the waveform as possible by filtering out whatever noise was there. So this is what a system, desirable system is. Sometimes, of course, not everything is desirable. So there are many cases where you have designed a system, but that system works for certain cases, and but for certain signals or certain scenarios, it behaves in an undesirable fashion. But let's stay like this. Let's just keep it at this, keep it simple. So the system is something which will manipulate your input signal and provide us with another output signal, which hopefully is what you desired. Now let's see where we should go to next. Okay, so yes, so we have continuous signals or analog signals, and we have digital signals. What is a continuous signal? A continuous signal is the best example we can. Let's stick to speech in this course. So pressure is changing as a function of time. So as you speak, just a minute. So as you speak, so what is happening here is the pressure is changing as a function of time. And that we represent with a microphone. We capture that and represent almost exactly the same waveform will come as a what is called voltage changing as a function of time. This pressure, we use a microphone, and that gives us the same signal almost, which voltage or current as a function of time. So we have, let's represent this ST. This is a speech signal. Now these are continuous signals. As you speak, it's not like you are speaking every millisecond or something after a gap of. You are speaking in a continuous manner. So that is why you will have, you can take any infinite number of values in any particular range, or in fact you can take any. If you shout loudly, it could go to any amplitude as high as you can shout, or if you whisper very slowly, its amplitude could be near zero, somewhere a number very very close to zero. So the whole real axis is available to you theoretically. Any value can come up during your when you are uttering a speech signal. And of course you are speaking continuously. In continuous speech, of course there will be silence in between, but nevertheless we record. Without silence also you cannot comprehend, specify, without any silence in between. If you just keep speaking, nobody will able to understand what you are saying. So it is a continuous time signal. So your time axis has also continuous values, and your amplitude axis has also continuous values. Now that is in the y-axis or the amplitude axis, their continuous values could be in a particular range. That will also give you infinite number of options, but it could also be any value, no limit at all, no bounds at all. But we have to process these signals via computer. We cannot store infinite values in a computer. Neither can any system process infinite values. A computer is a digital system. So what's a digital signal? Digital system will always process digital signals only. So every certain TS, sampling period we call, we sample the signal. We keep the values through an instrument called a sampler, some device. We sample the original continuous time signal at a certain period, uniform period, which we call a sampling period. And then what you will get? We'll get some a signal which has amplitude only at discrete time, only at certain, it is not continuous, only at certain intervals of time you get. That this could be infinite, but it is not continuous. This is not continuous. So at any, if you sample the continuous time signal at a particular interval called the sampling period, we'll get a discrete time signal. So this we represent is as a sequence of numbers n, and we represent it as Sn. If St was your continuous time signal, Sn will be your discrete time signal. So this is your discrete time signal. Now in the y-axis, the values this discrete time signal can have can still be arbitrary, could still be random. But if we quantize through a process called quantization, if we say no, we will not allow arbitrary values because that's also difficult to keep track of. We will keep track of these values in terms of certain bits. For example, if you want to have, let's say, 256 different unique values you want to keep in amplitude, you can represent it by then 8 bits for a single value. So because 2 to the power 8 is 256. So if you quantize it, so whatever value comes from the continuous time signal after sampling, from 0 to, let's say, whatever, 0 to 1, you pick a range and then you divide it into 256 different uh, segments, small segments. And this value, wherever it comes up, whichever is the closest level it matches to, we will set it to that. That is what is called quantization. And when you do both sampling and quantization, we convert the continuous time signal to a digital signal. Now, when we analyze signals, continuous time signal and digital signals, uh, we have techniques. We go to Fourier transform and all that. We'll discuss about that. But in case of digital signals, we generally, when we analyze them, we don't consider the effect of quantization because our analysis becomes very complicated. We just simply analyze them as discrete time signals. We will assume that whatever values in the y-axis it wants to take, the signal wants to take, let it be. We are only concerned that in the time domain, there are discrete, there are regular intervals. It's a sequence of numbers. Basically, the time axis is not continuous. Just like in image, for example, you have pixels. So y-axis and x-axis are not continuous. So in digital uh, a digital speech signal, you will not have continuous time axis. You will have a sequence of numbers. So let me erase. Okay. So till now, I think everything is quite easy, and you have been able to uh, grasp. If it's okay, type Y. Okay. So somebody has typed Y, so it's okay. So now let me come back to now then. What's a linear system? What's a linear system? So linear time invariant or linear shift invariant, also sometimes people say, for discrete time signals. So I said a system is something. Let me represent by xt, but if you want, you can represent by st also. Okay, let me represent by st so that you are not confused. St or Sn. Okay, so ht or hn. Yt or yn. So a system is something, discrete time or continuous time. You give an input, let's say speech signal, and you get an output. So we gave an example of a speech signal we recorded via microphone with background noise. Just simple example. We want to remove the noise, and so there is a system for that we have designed, and the output comes out noise free as much as possible. So now, what is a linear system? See, this kind of systems, a linear system is just if you have. So this is called the principle of superposition and homogeneity. So if you have a weighted sum of multiple inputs, if you have a weighted sum of multiple inputs, then your output should be also weighted sum of the outputs of the individual signals. This is all a linear system is. Now, a consequence of this definition is that if A1 and A2 are zero, if A1 and A2 are zero, so your input is zero, there is no input, you cannot have an output. The output also has to be zero. So that is why sometimes if you recall your signals and systems, sometimes you must have seen this example that there is a system such that if you give a signal xt to the system, the output comes out like a straight line. But because if c is not zero, c has some value which is not equal to zero, then what will happen is this is not a linear system. You can figure out why. If you put x1 and x2 as two inputs and their weighted sum, you will see they will not be equal because of this c term. So these are things, but that you can explore on your own as you browse back your old stuff, some systems. So I will come to now why linear systems, linear time invariant systems are very important. So this is a linear system. What about the time invariant? Time invariance is again the same thing. you give a delay, the output should be also delayed. So just by shifting the spoke uh, and you design a system which denotes the you spoke it the same utterance after 5 minutes, the system should behave the same. It will give the output 5 minutes later exactly the same. That's what all it means. So linearity, and this is time invariance. Now both these properties are required for some very useful analysis. It makes the system very useful for mathematical analysis and for engineering and signal processing. Non-linear systems are very very difficult to analyze and track and design and all that. Linear systems, we can at least do something about them, even if it is complex. So there was a person called Fourier, which you might know because of your you must have studied Fourier transform and all during your signal systems course. So what he observed that if you have a LTI system, and if you give some sinusoid, that output will also come as a sinusoid with some amplitude change. The amplitude will be changed by some factor, but the shape of the signal remains the same. So if you have an LTI system, and suppose you have sums of sinusoids, and you are somehow able to determine what will be the amplitude change, then you can basically predict what the output will be. So what he observed is, if you put a sinusoid, sine, cosine does not matter. If you put a sinusoid to LTI system, the output comes out to be the sinusoid with a change in its amplitude. So if you are able to find out somehow what the change in the amplitude will be, then we can basically, if you have a sum of sinusoids, we can find the result. We can find the predict the output. So if you have any arbitrary signal, this is an example from signals and systems you always get. A rectangular shaped function, rect. I think it is famously called, denoted as, if you have minus t by 2 to t by 2 with t, I think it is called rect t by t. I think it's, and if you have an amplitude of a, yeah, it's called a, is denoted like that. Most probably. In many books you will find like that. Does not matter. A rectangular signal. Somehow, if I can put this signal or represent this signal as sum of sinusoids, then I can also predict its output. So this is the intuition, or one of the intuitions behind Fourier analysis and the importance of LTI systems. In case of LTI system, we can predict the output. So Fourier came up with, I will erase again, any arbitrary signal. In our case, let's say the speech signal. So he came up with a method popularly known as the Fourier transform pair. I will represent this as a double arrow. Where he can represent this signal is a continuous time signal as a sum of sinusoids. So we generally write this as because this is a continuous Fourier transform I am representing. So this is your Fourier, and you can represent this. I think there is a 1 by 2 pi. I don't recall. Check this. But S of omega, it is got j omega t d omega. So your signal st is being represented by these complex sinusoids multiplied by an amplitude, basically a number. It is a complex number, but it's a number. So what is happening is your signal is represented in terms of sinusoids, infinite number of sinusoids multiplied by some number. Hence, if we pass this signal through an LTI system and use Fourier analysis, we can also predict its output. So that's the reason why we use Fourier analysis. Same thing goes for Laplace analysis. So again, I will pause for 1 minute. So did you get the intuition? Why LTI systems? If you got, just type Y. You've understood till now, I hope. So type Y. Yeah, okay. So now I will come back again. Now I represented this as a continuous time speech signal. Of course, now I said we have to sample, quantize, and do all that, and we will process digital signals. Computer can only do digital signals. This only in theory we can do. If you have certain specific signals in signal processing, you must have studied unit step function or exponential function and all that. There are some standard or sine and cos. There are some standard mathematical functions. You can get some standard solutions. But any arbitrary one, how do you? There is no standard solution. You'll have to use this integration. So how will you find it's an infinite integral? It's not possible. So for example, if you have a continuous time speech signal, how are you going to evaluate this integral? It's not a mathematical function. So anyways, even it was, it would have been a very difficult thing. So we process digital signals. So what we have Sn and you have n. And 0, 1, 2, some n minus 1. Let's say we were recording and we something. This n minus 1 or n length after sampling every ts seconds, we got this signal, a sequence of numbers. So we use our discrete Fourier transform, discrete time Fourier transform, not discrete Fourier transform, discrete time Fourier transform. So what it is given by, so again Sn S of e to the power j omega, or simply you can write S of omega if you prefer that. No issue at all. It's just a notational difference between continuous and discrete. So again, please check, there might be a 1 by 2 pi term. I don't recall. So you'll have S of, oh, sorry. So in continuous time, there was integration on both sides. But here we have a sequence of numbers. And integration and summation are equivalent. So what we'll have, if S of n e to the power minus j omega n, where n equal to whatever is your range, minus infinity to infinity. If your signal is only n points long, then rest will be zero when you have to do only finite summation. But this is the way to find out. Now, what is S of n? Oh, sorry. S of n is, so this is your S of n. Again, the same thing. We are representing the signal S of n in terms of a set of sinusoids, infinite number of sinusoids, and we have a amplitude for each of them. And hence we can use it in a linear time system and predict the output. Important thing to know here is the omega. In continuous time systems, there was no limit to as what frequency you could take. But in discrete time systems, omega always has to be within a period of 2 pi. It will be 0 to 2 pi, it will be minus pi to pi, which is generally considered. Why it is? In your assignment, you evaluate, because there are so many things to consider. In your assignment, you write all those stuff, write as much as you want. Next 15 days, I am giving you till 31st of August. Go through all that. Why discrete time signals is, and 2 pi, having a 2 pi frequency range. So let me see next where we can go. So there is not much time left. So next class then, what we'll do is we'll discuss Laplace and Z transform or Z transform. This is the most important topic, Laplace and Z transform. So next class we'll discuss that. So Z transform particularly will be very important in our case. I once again request you, please revisit your signals and systems, Laplace transform, Z transform, and Fourier transforms, and basic signals and systems, so that we can proceed with this course. Next week, I will most probably devote to revisiting these concepts, but after that, I will move straight ahead with our speech processing tasks. Anyways, I asked you to install Audacity? Did all of you install Audacity? Did you just record your sound and play around with it? Those who have, you can just type Y. I hope you install Audacity. Yeah, and my recorded lectures I think are available last week's whatever recorded lectures, or sorry, this week's previous two lectures. It's already recorded. You can again, those who were absent that day for whatever reason, you can go and check those lectures, and you will understand what I was trying to say. Before I leave, there is a important thing here. I almost forgot. Where is it? Let me. Yeah. So I will give you some very interesting, very intuitive videos. Please watch them, and it will also help in your understanding of your Fourier, clear your many concepts and doubts, and it will also it's called help in your assignment, writing your assignment. So some YouTube videos are there, some channels, technical channels that I followed. I thought it will be useful for you. There is this very good videos by Zack Star. He's also an engineer, so he has made some very good animations. So you go through this. You should have more intuition. It is a very preliminary way of visualization, but at least it will be something to help you, motivate you. Please watch these videos, and it will also help you in your assignment. Uh, and please revisit your signals and systems. Next week we'll focus mainly on this DSP fundamentals, and then we'll steam ahead with our signals and systems. Okay, then I will stop the recording. Please leave the lecture immediately.